Good afternoon. Is the slide visible?
Yes, sir.
Okay. Okay. Today we'll start a very important topic of machine learning, that is called overfitting. Now, these are the two main things we have to understand in this particular lecture, in this particular topic. First of all, what is overfitting, when it is happened, or when at least we understand what is our uh, classifier is overfitted. And if a particular classifier or particular model is overfitted, then how to handle it, how to fix the problem. Okay, so let's try to understand that what is overfitting is. Okay, so you see that this is the same problem of linear regression, and it is a housing price estimation problem. And we see that our hypothesis function is something like that, and the different hypothesis function. Okay. These are the three hypothesis function. And we plot this hypothesis function in this way, that for first, it is a just a linear, just straight line. Now, as you see that this is straight line, the equation is straight line. Now, the question is that the straight line is simple to implement, or computational complexity of this or of implementing this is very less, but the corresponding noise, this noise. So these are the actually these are the training samples. Okay, those which before even these are the training samples, and so this using this training sample we try to formulate this line, as we know that we discussed it, how actually we find it. We put a cost function and try to minimize the cost. Now, the idea is that the training error, if it is a kind of straight line, the training error, or better to say, this is a very simple. So in our next slides in this class, we'll say that this hypothesis function or this particular model, that model is going to represent these data samples are simple. So we can say the model complexity is low. Okay, so this model complexity is low means this model is a straight linear model, and generally you can say this corresponding error is in general or relatively high. So in that case, the training error, what is the training error? The error we are trying to minimize that error. That error is definitely after minimizing, when we convert that, or we can say that this is our final curve. This is relatively training error is high. So you can say that is underfit, and bias I'm coming later, but it's called underfitting. Underfitting means the data are or data samples or the labeled samples, training samples are not well represented. Now look at this curve. This curve is somewhat better to represent this data sample. So these corresponding error are minimized a lot. Sorry, minimized a lot. But you can say the model complexity, how you are going to measure the model complexity? By the degree of polynomial. So it is not a linear, it is a hypothesis function is polynomial. Polynomial degree, second order degree. So we can get this curve. So model complexity is higher than the previous straight line thing. But it is more or less represent the curve very accurately. Now another thing can be happen. Now if this is the curve, that you can say the model complexity is very high. So it's a multinomial representation or multinomial this curve. And so you can say that this curve is something like that. Okay. So this is a very complicated curve. Okay. Now the question is that now we say it is overfit. Now what do you mean by overfit? Now we already discussed thing. We again discuss this thing. Let this is the kind of okay. Now if you say that okay, we use a kind of curve like this. So this is a more or less the curve. The curve is more or less accurately represent this point. Okay. And of medium complexity, model complexity. Now if you say there is a point here. But the question is that how you change this curve? Are you going to say the same curve, just neglecting this particular point? Otherwise, you can do something. This definitely this curve, the model complexity is high, is too high. Okay. And it, so if it is though the training error is less. But one thing happened in this case, that it, by considering all the points, it may be the training error may be very less, but it lose the generality. Now what do you mean by generality? Generality means you just see the curve. This curve is essentially going to cover or represent these points, assuming that these data points are kind of obeying some distribution. And this is not a very random distribution. It is not very random in nature. Okay. But if some sort of hypothesis function, which may be very accurate to all the data points, but these data points, particularly this, it is not very much synchronized with other data points. And to in considering this data point or represent this data point also, this curve, although it is very accurate for the given data points or the given data samples, it loses the generality. That means now if you try to understand what is that, what is the generality in that, we have to understand that what kind of a test sample will come. Now again, I give you example in that you can understand it very. Now this is the space, and this is the curve. Okay, and there is another point here. So one data point is something like that. This is the curve. So if this is the training kind of thing, you omit this. Now if your test sample is something like that, okay, then these state samples, the error of this state sample is somewhat very in sync with these data points, data samples. But if you consider this thing, then maybe this may be the thing. This is the line. Now you see that the data samples as the this is the testing error will be large than the previous thing. Okay. So this is the thing that you can, maybe the training error will be very less, but by making the training very accurate, we are increasing the model complexity, and as it same time we lose the generality. That means generality is a natural tendency of the data clustering or data distributions. Okay. So another example I'm trying to say here that you can understand it much clearly. That let's say this is the example. Now that was the regression. Now I put a classification. Okay, and here this is one. So this is the your kind of distribution. Okay. Now, if this is the distribution, the natural clustering, so that so the decision boundary is something this. Okay. Now, you can say this decision boundary, let's say it's a linear. So the model complexity is of this decision boundary is somewhat less. Okay. But we don't consider this point. We put this is outlier or is a noise. Okay. But another thing we can do, that we can do something like that. This kind of thing can be possible. It can be very, if the model complexity for this model complexity is high. And now the question is that if there is a data point here, now testing data I'm saying, now the testing data is in this. Okay. So should I call it, sorry, I should write, I write wrongly. Yes, it is testing data in here. Okay, this is the testing data. Now, should I call, but in for our high model complexity, it is in this group, this class belongs to 0 class. But if we use our normal complexity, it is this class, this belongs to cross class. Okay. Now, what it should be? Now, you see, these particular data points have a kind of some sort of clustering like this. Okay, and these data points are clustering in this. Okay, so even if this is a very highly accurate for with sake of or with respect to the training, but it loses the generality of the given data points. Now you understand what is generality means. And in this case, if this happened, there is a lot of symptoms of your training error, testing error. Just for example, I will give the more formally, more mathematically in the next few slides. But from a simple example viewpoint or simple understanding viewpoint, if the training error is very less, but testing error is not that much good, then we say the model is overfitting or this model is overfitted. Okay. So if you have any question, you can ask, because this is very, very interesting or very important also.
Excuse me, sir.
Yes, please.
Sir, in the right it is written overfit or high variance. Could you tell
No,
what is it?
I'm fine. I'm a bias variance. I didn't come. I'll come.
Oh,
Don't please.
okay.
I'm not defined yet. I'll come after 2, 3 slides. I'll come. What is bias? What is variance?
Oh, okay. Thank you, sir.
Yes. So conceptually, it is understandable. And I didn't anything. No mathematical. No example. Nothing I have said. I just I just said the very naive, very common sense concept. And because this is important, ultimately we will this particular intuitive or intuitive concept will going to prove in a different way, different other strategy and how to all these things will done. But this common thing is very important, because you are going to when you are going to uh, design a network, maybe deep, maybe shallow, whatever you want for a particular application, then you have to understand this from the very common sense viewpoint. All these things are there, but that mathematical formulation, uska jo symptoms say what we'll do, what are the different reason why we do that, all this mathematical justification, all this man, wo to hai. तो बाद में देखूंगा, but the common sense simply when as a coding viewpoint, this is the major thing. Okay, so if it is clear, then everything will be very easy for you. Okay, so by definition, I write a lot of things here. Just let me omit all this. Okay, so it is said if we have too many features, the learned hypothesis may fit the training set very well. That is that this is your linear regression cost function. It may comes very close to zero, but fail to generalize the new samples. I mean testing samples. So predicts price in new sample. This failed to generalize means failed to predict. Okay. So as a very good approximation, very simplistic, you can say, we generally try to represent or model the underlying distribution or the pattern, not all the individual data points. The pattern is important because it is assumed in the supervised setting or in even other settings also that in general that testing sample is also coming from the similar distribution. So if you the distribution pattern, if we follow, then it well generalized, assuming that the testing samples are coming or follow the similar distribution. Okay. Okay. Now the same thing, the same example we give for the logistic regression. You see, this is definitely underfit, and this is somewhat we desired, and definitely this is a this is actually a bit wrongly it is coming. I don't know why. It is something like that. So this is actually trying to say. Okay. So this they definitely overfitted. And this is bit underfit, you can say. Okay. So the same example. Okay. Now the question, what is bias, what is variance? Now I just first read out, then explain. What is bias? So the bias is the difference between the average prediction of our model and the correct value which we are trying to predict. Okay. So that is the basic understanding, that somewhat it is that difference with the average prediction of our model. So एक model जो हो रहा है, we can say that we have a kind of average. This is the okay. Now it is very easy to understand from that. This is the your prediction. This is, let's say, average prediction kind of thing. And what is the difference between this? So these differences. You can say something the cost function for your understanding, but it's not the cost function. Bias is the difference between average prediction of our model. So actually, what are the average prediction of this? Maybe somewhere here, maybe somewhere here, maybe somewhere here, or something like that, which we are trying to predict. Okay. Model with this high bias pays a very little attention to the training data and oversimplifies the model. So definitely, the model complexity is too low or very simple to represent the data points, the data samples accurately. Okay. So we do not, if we say that something like that, this is the data point, and if this is your prediction. So this is a somewhat bad prediction, or this is overfitting. It's not underfitting. So what is bias? Difference between the average prediction. So this is something average. Average prediction is very bad. So difference means this difference is high. So high bias is EA important is basically underfitting. Is basically it has a tendency to underfit. And definitely, if there is a lot of training error, testing error will be very high. This is called bias. Now, what is variance? Variance is the variability of the model prediction for a given data point or a value which tells us spread of our data. Okay. Model with high variance pays a lot of attention to training data and does not generalize on the data which it has not seen before. As a result, such a model performs very well in training but has high error rates of the testing. So exactly variance, I write reading it again, read it again. Variance is the variability of the model prediction. So now the question is that this is bit complicated to visualize. Now you say that now if this is the data and if this is sorry, if this is the data and let this is the your. Now the question is that this this thing is not a that much high variance. But if it is that it is a very high variance, so there is a lot of this thing. Let's say it's much it more easily understood in this case, where we have a kind of a some sort of noisy kind of data. This is the normal, and there is a, some sort of this data is there. So if we say that our data is something this, yes, this kind of thing. Now, if this is your curve, this curve is a very high variance. Now, okay, that why is high variance? The variance, the variability of the model prediction. So this is the model prediction. So that the model, this is the model or hypothesis function or a particular function that describes your model that is very much variable in nature. ये बहुत उसका high frequency थोड़ा ज़्यादा है. prediction given a data point or a values which tells the spread of the data. So the spread that we are very much acquainted with that. But in that sense, if we say, okay, we will do it in this way, we don't care about these two values and we do this kind of thing, then this particular thing as a kind of low variance. You see, low variance has somewhat high error rate in training cases than this high variance counterpart. But it more generalized because it is, I said, it is assumed or it is expected that the testing sample follow this kind of distributions. Similar, not here, it is expected. Okay. So as a result, such model, that this variable kind of model, this green card model, performs very well for training data because training data, look, errors is very less, but that performs not good for testing data, assuming the testing data are following the similar distribution of the training data. Getting the point? In that case, these two are not following the distribution. Training is the kind of a outliers. Outliers. Now, it is clear to everybody what is bias, what is variance? Because there's a lot of questions coming in from here. different इसका bias ज़्यादा है, उसको variance ज़्यादा है, क्या है, क्या क्यों है, कौन bias ज़्यादा से होने से underfitting है, वो मैं दिखा रहा हूँ, और ज़्यादा variance होने से overfitting है, और क्या है ये थोड़ा देखना है. Now bias variance using the Boole-Eyes diagram. Now you see that if it is high bias, now it is basically a kind of diagram. Center of the target is a model that perfectly predicts the correct values. So this center is basically, actually we try to fix our prediction within the center. Okay. The center of the target is model that perfectly predicts the correct values. As we move away from the bullseye, that means here, this bullseye, then our prediction become get worse and worse. So that is the idea. If you go from here to here, our prediction is bad. Both training, testing. Now you see, in supervised learning situation, underfitting happens when the model unable to capture the underlying pattern of the data. So this is the case. This is the data and this is your prediction. It's not that much well. This is underfitting. Now, if the underfitting is that you can say what is usually the high bias and low variance. You can say that this high bias, so this is the underfitting. So this is high bias, okay, but low variance. Now, what do we mean by high bias? High bias means it is not well predicted. So low bias होने से ये यहाँ पर आ जाएगा. And low variance means what? Low variance means that it is clustered densely. So variance, not that much variant is. So it is not a very high variance thing. If you see here, I think you can understand. From here, variance is less, but the model itself is bad. So it is clustered well, but it is out. It is very long distance from the actual prediction. It's called underfitting. What is intended? Low variance and low bias. You देखो, low variance is cluster is very, and low bias when it is very accurately predicted. So something this. If you say something like that, is low variance, low bias. Okay. Now you see, high bias, high variance. Now high bias means it is the center is very here, and now variance is also high. So you see the distance, average distance is also very high. Okay, from this cluster center. So this high variance. So that's why high variance. Low bias, high variance. Low bias means what? It is more. It is okay. Cluster center is here, but the variance is very high. So that means we are understand the data is well, but the problem is that due to this we are understanding the data well, but we are going for there is a lot of variance of this curve is very high. So you can see the variance is very high. So these this is the variance. So these are very also high. So it happens very when we very less amount of data. This is this is called high variance and low, high bias, low variance. High bias, low variance is underfitting. And what is overfitting? Yeah, you can understand. In supervised learning, overfitting happens when our model captures the noise along with our underlying pattern. So this is the high variance. You know that this is a more noisy kind of. These are the more noise kind of. But we are going to zigzag. So variance is very high. So exactly this is the thing what I said lot of time. So this is the thing. If we go in this way, this is high variance. So this is basically high variance and low bias. So that this is training error. Low bias means training error is less, and but high variance is that the testing error is also very high. So overfitting happens when our model captures the noise along with our underlying pattern in data. So if it is noise, we also capture the noise. It happens when we train our model lot over noisy data set. This model have low bias and high variance. So that is important. It's a low bias and high variance. Go back to this diagram, low bias, high variance. This is overfitting. Low bias, high variance. Okay. These models are very complex, like decision trees, which are prone to overfitting. So you can see that high bias, this is underfitting, this is our intended, and this is very overfitting. This is a lot of zigzag thing. Okay. And this is very important. This is called bias variance trade-off. So what we important is that how much low bias, low variance. That is intended. Now, if you have any question, you can ask. Okay, very good. Now, it is very this particular slide is important because here we formalize a practical machine learning model. Formalize in that sense, kind of try to understand what practicality in practical what happened. So why bias variance trade-off? So we are trying to understand there is a trade-off between bias and variance. Okay. If our model is too simple and has very few parameters, simple means what? That means you can say simple means if you say straight line is a simple. So how many parameters? Y is equal to mx plus c. This is your straight line. Now this is theta, let's say theta g1 and theta 0. Two parameters. So very less number of feature, very less number of parameters are there. But if you say that, okay, y is equal to ax square plus bx cube plus cx4 and so on. So it's a very multinomial or polynomial kind of expression. It's very complex. So definitely it is, since it is a, so there's a degree of curvature is increased, something like that. So model complexity is become higher and higher. So model complexity is increasing. Increasing. Okay. So we say if our model is too simple and very few parameter, less complex, it may be high bias. Definitely, it's a high bias. You can count. High bias means what? This is the situation of high bias. So high bias means it is concentrated well. Okay, but low variance. Sorry, high bias means it is over. It is not that much accurately predicted. So very simple. So it cannot very close to actual intended. That is high bias. And low variance, it is concentrated. So, so that is high bias and low variance. High bias means this is the high bias because it is not, the error is not that much well accurately predict the data sample, training sample. That's why it's a high bias, and low variance, it is clustered properly. On the other hand, if our model has large number of parameters, now this kind of thing is highly complex, model complexity is too high, then it's going to high variance and low bias. Now high variance means, so it may approximate the training sample very well, but it also approximates the noise, so it loses the generality. Okay, and if it loses the generality, the testing error will be very high. Okay, and it is called overfitting. Okay, that's why they say it's going to have a high variance, low bias. So we need to find the right and good balance without overfitting and underfitting. So high variance, low bias भी नहीं चाहिए, high bias भी low variance भी नहीं चाहिए. So low variance भी नहीं चाहिए, high variance भी नहीं चाहिए, low bias भी नहीं चाहिए, high bias भी नहीं चाहिए. So something in between हमें चाहिए. So what is this? Low bias, low variance. Okay. This is low bias, low variance. So this is our intended. This trade-off in complexity is why there is a trade-off between a bias and variance. Algorithm can't be more complex and less complex at the same time. Okay, so you can say that the kind of thing, the error, actually the error is basically this, that you can say this is the bias curve, this the white curve, and this is the variance curve. Okay, and that is somewhat meeting here in this. Okay. Okay, this particular, this is actually the point of this. I think you can understand the optimal balance is there. This follow this line, and you see the total error is basically reducing because bias is reducing. So that means, so this is the bias, so bias is also reducing, and here you can say it is bias is very much, that much low bias is not required. But again, you can say variance is basically again reducing, but here it's become very less. So this is the optimal point. So the total error is minimum here, and then it start. So at this point, up to this point, it is that the when your model complexity is getting higher and higher, that is less. After if it is more complex, the overfitting started. So that is understand, that is the basic optimal balance point, you can say. To build a good model, we need to find a good balance between bias and variance such that it minimizes the total error. So this is bias. This total error is bias to this bias square plus variance. The irreducible error is there. There is some error is inevitable kind of. You cannot get rid of this error. So it's called irreducible error. An optimal balance of bias and variance would never overfit or underfit the model. So that is very important to understand. Now you can say the total error. So this is actually the complexity is getting higher and higher. So that is very important to understand. Now complexity is high in this, but this complexity higher means this is just for example. First this is the straight line, then it is a something curve. Now this is the something curve. Now it is more. This is complexity. So this is the complexity is basically increasing. So it is the model complexity. So at this particular complexity, the optimal this of the error is least. If you again complexity higher, it will start increasing. So that is the trade-off. That this may bias be low hai, variance be low hai. So low bias, low variance, we can get a optimal function. And this is called the bias variance trade-off. Is there any question you can ask? Okay. So, but the overfitting, how we are going to define overfitting? A hypothesis function H is said to overfit the training data if there is another hypothesis H bar such that H bar has more error than H on training data, but H bar has less error than H on testing data. So there is if there is H is hypothesis function for your model, and if there is H bar is another hypothesis that's present, training error of H is less than or H bar. So this is that. If there's another has that H bar is it, the H bar has more error H on training, so it is more error in the training, but testing error of H greater than H bar. If both these two conditions occur simultaneously, both holds, both hold, then it's called overfitting. Then over. Learning classifier that classify training data perfectly may not lead to the classifier the base generalization performance. So that means this overfit, this actually this model is overfitted. H is overfitting by H. Overfitting by with respect to H. So learning a classifier that classifies the training data perfectly may not lead to classifier with the best generalization performance. That means this training error is very perfectly represent the training sample, but not necessarily because the testing error is high than this other hypothesis function. So that means that it not generalized well, or at least there is some hypothesis function that generalize well than this. Okay, there may be noise in training data, that one thing, and training data set is too small, so that is very important. That is more practical when you are that is a very fundamental suggestion or a very practical suggestion, I should say. When you are going to design a deep learning thing, because people nowadays everybody not no, nobody is going to and design a SVM or something. I mean, most of the time it will going for a deep learning because everybody is doing deep learning. But you have to be very careful. If you don't have sufficient data, don't make your network very large, very large. Then it's definitely worth it. Okay, so if model complexity is too high, then your data is annotated data, correct data is very noisy data may be problem, but correct data is very small. Then better not to design a very large network. It easily overfit. Okay, it's a practical suggestion. Okay. Simplistically, overfitting occurs when model is too complex, while underfitting occurs when model is too simple. So we have a kind of idea that in between we have to choose. Training error is not a good predictor for the testing error. Definitely. जो ट्रेनिंग एरर कम है तो हमारा मॉडल अच्छा है, देयर इज नो मीनिंग ऑफ दैट. Ultimately, model is being evaluated on the basis of testing error, not on the training error. That is the very important thing to consider in this machine learning thing. Okay, so you have any other question, you can ask. Okay, we stop here today. We'll continue this thing in the next class. Thank you.